this video, I want to talk about a third method for solving dynamic problems. And this method is using momentum as a means of analyzing a problem and looking at what's going on. And the utility of this method is that it provides a slightly easier way to look at problems that involve forces being applied for short time spans. So think of things like impact, like a baseball bat hitting a ball. That's a short time over which a force is applied, and using the concept of momentum kind of helps us analyze that system. So to start with, we're going to recall that, I didn't write that very well. We have our basic equation F equals ma. Now, knowing that acceleration is simply the first time derivative of velocity, we can rewrite this equation by taking and substituting in that time derivative and then writing this as mass times velocity. Now, this term here, this mv, is specifically linear momentum. So that's the momentum term that we're going to go ahead and make use of. So we've got this equation now that F equals the time derivative of momentum. So we can rearrange that equation and we can write it as F dt equals the differential of momentum. Now if we integrate this, so our next step is going to be to integrate, and we'll do it with respect to time and with respect to velocity. So we have the integral from t1 to t2, so over some split in time of f dt, and we do the same of mass with respect to velocity, and we'll just say we're going from v1 to v2, so we're experiencing some change in v. This right hand side, I can evaluate the integration and end up with mv2 minus mv1, and I'm going to leave the left hand side for now. So if I take this and rewrite it, I'm going to write it as mv1, and we'll note that that's a vector, plus the integration from t1 to t2, f, which is also a vector, dt equals mv2. So what this looks like, at least when I look at it, it looks very similar to our conservation of energy equation, where we saw that we have some initial state of energy, we add something into it, and we get a new state at the second time step. And that's kind of what we're seeing here. We have some initial momentum, we add something to it, and as a result we have some new momentum. This thing that we're adding to it, this middle portion here, we're going to call impulse. And this impulse is the addition of a force over some time step. So it is force applied over delta t from t1 to t2. And I'm going to write it as IMP for impulse. It has units of Newton seconds. We can see that from the equation, right? It's a force times a time. Newton seconds would also be equivalent to kilogram meters per second squared if we break apart the newtons, times seconds, which means it's equal to kilogram meters per second. Useful to kind of know how this is written in kind of its base unit so that we can, evaluate our equations for unit consistency. So in words, what this says is that a moving object or an object that's acted on over a period of time by a force will experience a change in momentum. It'll go from state 1 to state 2 where velocity has changed from v1 to v2. So I'm going to rewrite this equation kind of using that notation. mv1 plus impulse, which is itself a vector, equals mv2. And this vector notation should tell us that we can express this equation in Cartesian coordinates or whatever coordinate system we have to be using in order to put this all together. Now we should also note that I can also write this as a summation of impulses, meaning that it doesn't have to be just one impulse that's having an impact here. We can have more than one force involved. So the equation could look like that, and that's those several forces being added together. Now, if we have no external forces, I'm just going to kind of do this off to the side. If we have no external forces acting, then we very easily can see that we would have mv1 equals mv2, which is basically just conservation of momentum. If there's nothing acting on the system, then momentum has to be conserved, and we can evaluate that over a range of things. Now, I've already shown that we could include this summation here if we have multiple forces acting on a system or on an object. However, we could also write this for multiple objects, which is to say we have two different particles, each with their own momentum doing something, and we want to treat that as a system. We can write this with summation terms for each expression in this equation. And what this says is that I can have more than one thing involved, and I can sum the momentum of each thing, sum the forces that might be applied externally, and then finally sum the resulting momentums after whatever happens. So kind of an interesting example of this would be two billiard balls coming together. They each have their own momentum, they make contact, and then they separate with different momentums, different velocity vectors. And in that case, we don't really have any external forces involved directly, if we neglect friction and things like that, but we have individual momentums being brought together and then going their separate ways. And we can use this conservation of momentum principle to analyze that. Now in that example I just gave, this impulse term right here in the middle would be zero if we don't have those external forces acting. So we can just keep in mind that impulse may or may not exist depending on whether or not we have those external forces. All right, so we will look at how we can actually use this to analyze problems involving impact and how that plays a role in what we would look at for dynamic situations. All right, thank you.